Mga migs, welcome to Winnie Luna Nahir Eduk channel on mathematics and other related topics. In this video, we are going to discuss probability, permutation, and combination. These are very important topics in the next chapter of our journey. Now, let's have probability. The importance of probability lies in its role in inferential statistics. While statistics focuses on its use of information concerning a sample to make inferences about the nature of the population from where it is drawn, probability provides a measure of certainty attached to the statement regarding the population. So, it is quite clear that understanding probability is very important in doing decision in inferential statistics. What I mean is in making a conclusion about the characteristics of the population using the sample we get from that population. That is why we have to understand probability so we could understand what is meant by probability value by the time we are going to decide if we are going to reject or not the null hypothesis in our research work. Probability is a possibility or a chance to be true or to happen. Then we have here some terms that we have to understand. Randomness of sampling as the best introduction to probability concept is meant to promote more rational statistical decision making under conditions and uncertainty. So we have to take note of this word randomness. Randomness. Then any activity or process that has a number of outcomes is called an experiment. So there's an activity or process which provides outcomes. We call that one experiment. An experiment is often conducted in several trials to generate a set of data. It is a sort of prediction after several trials with a chance result. The result is stated in fraction, decimal, or in percent. Then the set of collection of all possible outcomes of an experiment is called sample space. So we have to understand the terms that we have defined here so we could really understand what is meant by probability. The sample space of an experiment consists of elements or sample points such that to reach outcome of the experiment, there corresponds exactly one element in the sample space. Now, for this particular terms, it's just like tossing a fair coin once. Okay? So, a fair coin has two sides. You have the side of a tail and the side of a head. Now, these two become the elements or the sample points. And in the activity that you will do, tossing a fair coin once, it is only one will come up. It's either a head or a tail. So for that, you have the elements in your sample space and then only one of those elements contained in the sample space will come out. So we will have illustrations for this. Now, sample space is denoted by this symbol, omega, or we can just use the uppercase letter S. Tree diagrams, tables, and graphs are often used to represent the outcomes of experiments to facilitate counting of elements of sample space. That is, that is very true because we cannot determine the probability for an event to happen if we cannot exhaustively determine all the elements to be contained in the sample space. Now, we have experimental probability. Experimental probability is a statistical expression of the prediction made from experiments with definable results. It is a process which is repetitive in nature but provides well-defined results. For this, the formula is this one. P sub S equals N sub ST over Tn sub Tm times 100, where P sub S, that is our probability of success, N sub St, that is the number of successful trials, then Tn sub Tm, that is the total number of trials made. Okay, so this is our formula for experimental probability. Now, we have here a comparison between experimental probability and theoretical probability. So, let's understand this one. For experimental probability, it is based on the data which is obtained after an experiment is carried out. Of course, as what the title has suggested, so there should be an experiment to be conducted. However, in theoretical probability, this is based on what is expected to happen in an experiment without actually conducting it. So, it has or it is also aligned to the header theoretical probability. So in this, there's no experiment being conducted. It is just expected. It is just expected. We can even consider tossing a fair coin once. That's to fall under this theoretical probability in the sense that we have the idea that a fair coin has two faces, the head and the tail. So we can expect that out of those two possibilities, one will surely happen. Okay, the next, under experimental probability, it is the result of the number of occurrences of an event divided by the total number of trials. While in the theoretical probability, it is the result of the number of favorable outcomes divided by the total number of possible outcomes. Okay? So, theoretical probability does not do an activity. They are just expecting. They have it has the idea of the possible outcomes. So we have here an illustration. Okay, here a coin is tossed 20 times. it is recorded that heads occurred 12 times and tails occurred 8 times. So the probability of heads is equal to 12 over 20, or that is just 3/5, because 12 and 20 have a common factor, which is 4. 12 divided by 4, that is 3. 20 divided by 4, that is 5. Then P of tails is 8 over 20. So that is 2/5, because 8 and 20 have also a common factor, which is 4. So 8 divided by 4, that is 2. 20 divided by 4, that is 5. Okay, so in this illustration, there was an activity being conducted. The results were recorded, the results were observed, okay? Because a fair Cohen, we can say it's a fair Cohen because there are occurrences for the heads and occurrences for the tails. So there was an activity. Under theoretical probability, as what I said earlier, a coin is tossed. So it is assumed that this coin is fair. So the probability for a head to come up is just 1/2, because there's a single tossing of coin. The possibilities are for the head to come up or for the tail to come up. So in your sample space, there are two elements. And out of those two elements, only one will happen. That is why the probability of a head is 1/2, and the probability of a tail is also 1/2. Okay? So that's the difference between experimental probability and theoretical probability. Now, let's have examples of experimental probability. We have here the number of cookies made by Patrick per day in this week is given as 4, 7, 6, 9, 5, 9, 5. So, these are the cookies made by Patrick per day in the previous week. Let's just say in the previous week, because the number of cookies being made is recorded. Now, based on this data, what is the reasonable estimate of the probability that Patrick makes less than 6 cookies the next day? So this is 1, 2, 3, 4, 5, 6, 7. So this is the recorded data about the number of cookies in 1 week, made in 1 week per day. Now, the question is, what is the reasonable estimate of the probability that Patrick makes less than 6 cookies the next day? So if Patrick started recording the cookies he made, say, Monday. So Monday, 4 cookies. Monday, Tuesday, 7 cookies. Wednesday, 7 cookies. Thursday, 9 cookies. Friday, 5 cookies. Saturday, 9 cookies. Sunday, 5 cookies. So the problem is about estimating the number of cookies the next day, which is Monday. So these are the data that we are going to use to estimate the number of cookies to be made by Patrick. But in this particular problem, our our estimate is on the number of cookies less than 6. Less than 6. Okay? So, P, the probability of making less than 6 cookies. So, this is the symbol. Probability of making cookies less than 6 is equal to 3 over 7. Why is this 3 over 7? Now, look at the data. There are 3 instances in which Patrick made less than 6 cookies. This 4, 5, and 5. So 3 over 7, the decimal equivalent is 0.428. And if we are going to round this off to change this to percent, you move this decimal point 2 places to the right and round it off to a whole number. So you have 43%. So that is our reasonable estimate that Patrick will make less than 6 cookies the next day. Next, consider here this one, this table. We have the header of pizza toppings and the number of orders. So we're talking about pizza toppings. I believe that you really like pizza. Now, for mushrooms topping here, there were only 4 orders. Then pepperoni, 5 orders. Cheese, 7 orders. Black olives, 4 orders. So this is our reference in the next problem. So here, find the reasonable estimate of the probability that while ordering a pizza, the next order will not be of a pepperoni topping. Will not be of a pepperoni topping. What does it mean? It could be mushroom, cheese, or black olives. So that's the idea. Based on this data, the reasonable estimate of the probability that the next type of toppings that would get ordered is not a pepperoni will be, so look at this, black olives, 4, cheese, 7, mushroom, 4. Take the sum of the orders, that is 15. So you have 15 over 20. 20 because 4 plus 5 plus 7 plus 4, that is equal to 20. So 15 over 20, the numerator and the denominator have a common factor, which is 5. 15 divided by 5, that is 3. 20 divided by 5, that is 4. 3/4. And 3/4 is equal to 0.75. 0.75 is equivalent to 75%. So we have this estimate. No, we are 75% sure. No, we have that belief that the next topping to be ordered is not a pepperoni. Okay, so this is just an example of an experimental probability. Now let's come to addition of probabilities. Addition of probabilities. This is a very important topic also. Probabilities can be added when a set of mutual events can be specified. When the probabilities associated with these events can be stated and when the probability associated with a subset of these events is required. So there seems to be terms to be added, no probabilities to be added. That is why addition of probabilities. For us to understand clearly on this, let's have an example. Okay, here. If you take out a single card from a regular pack of cards, what is the probability that the card is either an ace or spade? Now, take note, there's or. Ace or spade. Now, let X be the event of picking an ace and Y be the event of picking a spade. Now, P of X equals 4 over 52. Why? We say here, X be the event of picking an ace. In a regular pack of cards, there are 4 aces. That is why we have 4 over 32. Now, for Y, the probability of the event of picking a spade. So, P of Y, this Y stands for spade. So, that is equal to 13 over 52. Because in a regular pack of cards, there are 13 cards which are spades. Okay? Now, these two events are not mutually exclusive. Let's understand this one. Why are these two events not mutually exclusive? They are not mutually exclusive because for the spades, one of them is an ace. It seems, or it is absolutely clear that these two events share a common card. That is the ace. So ace is counted in here, picking an ace, and in here, picking a spade. So as there is one favorable outcome in which the card can be both an ace and a spade. Okay? An ace and a spade. So, the probability of picking an ace and picking a spade is equal to 1 over 52. As what I said here, they share a common card. So that common card is that card which is ace and a spade. So for this, you have 1 over 52. Now, the probability of picking an ace or picking a spade is equal to, so you have to add it here, 4 over 52, then 13 over 52, then you subtract that probability, this one, the common card, subtract the probability of getting a common card. So you have, copying the denominator, the common denominator, that is 52. Then 4 plus 13, that is 17, minus 1, that is equal to 16. Then 16 and 52 have a common factor, that is 4. 16 divided by 4, that is 4. 52 divided by 4, that is 13. So, what is the probability that a card is either an ace or spade? You only have 4 over 13. That's our probability. So, the answer was given in terms of a fraction. And you can change that one also into percent. Now, let's have another example. What is the probability of getting 3 heads and 3 tails if a coin, so it is assumed again that the coin is fair, is tossed 3 times. So how many times? 3 times. Okay. Solution. We know that when a coin is tossed only once, then the sample space is head, tail. So this is what I said earlier. If a fair coin is tossed once, the sample space will contain only the head and tail. However, in this problem, you are going to toss the fair coin 3 times. This means that we can get either a head or a tail when a coin is tossed once. Now, since the coin has been tossed 3 times, hence, the total number of possible outcomes would be 8. This is because of the fact that when a coin is tossed in number of times, then the total possible outcomes are 2 raised to n. Hence, sample space is, so we're using here the uppercase letter S, not the Greek letter omega. So S equals, okay. So these are the elements of the sample space. The elements that I'm referring to are the possible outcomes contained in the sample space. So, these are the possibilities. First toss, it's ahead. Second toss, it's ahead. Third toss, it's ahead. It could be also that the first toss is ahead, the second toss is ahead, and the third toss is a tail. It could be that the first toss is ahead, the second toss is a tail, the third toss is a tail. And then the first toss is a tail, the second toss is a head, then the third toss is a head. It could be that the first toss is a tail, the second toss is a tail, and the third toss is a head. Or it could be the first toss is a tail, the second toss is a head, and the third toss is a tail. Or it could be the first toss is a head, the second toss is a tail, the third toss is a head, and the last one, the first toss is a tail, the second toss is a tail, and the third toss is a tail. Therefore, the total number of possible outcomes is 8. Hence, the probability of getting the 3 heads is equal to 1 over 8. 1 over 8. And the probability of getting the 3 tails is also 1 over 8. Getting the probabilities of 3 heads and 3 tails when a coin is tossed 3 times can be done by getting the sum of the individual probabilities. So what are the individual probabilities here? The individual probabilities are the getting of the probability of 3 heads, that's the first one, and the second one is the probability of getting 3 tails. Now look at here. This one, this is the first, then the second, 3 tails. This one, 3 tails. This one. Okay? So just take the sum. Okay? So 1 over 8 plus 1 over 8, that is 2 over 8. 2 and 8 have a common factor, which is 2. 2 divided by 2, that is 1. 8 divided by 2, that is equal to 4. Okay, so the probability is equal to 1/4, or that is just 25%. Now let's come to permutation. Permutation is about arranging items or objects in a definite order. If there are n times to be arranged all at the same time, and none of these items should be repeated, the number of permutations is computed by taking n factorial. This is read as n factorial. The formula is as follows. We have here, you read this one as P of R, P of n taken R at a time. So you read that one, equals n factorial over n minus R factorial. Okay? Where n is the total number of objects, R is the number of objects selected. Then the generalized expression of the formula, how many ways can you arrange R from a set of n if the order matters? A permutation can be calculated by hand as well, where all the possible permutations are written out. So you can you can calculate, no, the permutation by hand. Illustration or example. Here, how many three-letter words with or without meaning can be formed out of the letters of the word swing when repetition of letters is not allowed? So take note, repetition of letters is not allowed. So in this word swing, you cannot repeat S. You cannot repeat W. You cannot repeat I. You cannot repeat N, nor repeat G. Okay? So, three-letter words with or without meaning. That means just arrange the words using three letters from the word swing. Okay? Now, how many letters are in this word swing? There are 5. Okay? As the word swing has 5 letters. Since we have to frame three-letter words with or without meaning and without repetition, therefore, total permutations possible are this one. P of 5 taken 3 at a time equals 5 factorial over 5 minus 3 factorial. So, when you say 5 factorial, it is just the same as you are taking the product from 5 up to 1. So, in here, you have 5 times 4 times 3 times 2 times 1. 5 minus 3 is 2, so you have 2 times 1. Okay? So, take the product here. 5 times 4, that is 20 times 3. That is 60 times 2, that is 120 times 1, 120. 2 times 1 is 2, so 120 divided by 2, 60. 60. So, this means that using this word swing, and you are to form or frame three letters coming from this word swing, you can make 60. You can frame 63 letters out of this word swing. So this is the what we call result. This is an illustration of permutation. There is another way, no, there is another way of doing this one. We call this one the multiplication rule. Okay, let's have, okay, uh, choose a color that is, uh, let's let's have a color is that is really visible. What's happening? Okay, since we have to frame three letters coming from the word swing, we have to make here three blanks. Okay, so it is like this. There are five letters in swing. Now, for the first blank here, you have how many choices of the word that you will place over here? You have five choices because there are five letters in the word swing. So you write it here, five. Okay? Since repetition is not allowed, for the second blank, how many choices do you have? There are only four. Because one of the letters of the word swing is already used here in the first blank. Okay? Now, for the third blank, you choose a letter. But this time, how many are left? A letter is used in the first blank, and another letter is used in the second blank. So, of the five letters in the word swing, only three are left. So you have here three choices. Now, by multiplication rule, 5 times 4, that is 20, times 3, that is 60. So you can approach this kind of problem using the multiplication rule. Another example of permutation. How many three-letter words with or without meaning? So just framing a three-letter frame three letters or can be formed out of the letters of the word smoke when repetition of words is allowed. So this is now different, no? This is now different because you can repeat. So in a letter you frame, you can have S, 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 M, 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 O, 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 K, 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 E, 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 because repetition is allowed. Okay? The number of objects in this case is 5. As the word smoke has 5 letters or alphabets, and your R is 3 because only 3 letters are to be framed using the word smoke. As 3 word has to be chosen. Thus, the permutation will be when repetition is allowed is just 5 cube or that is equal to 125. To understand more why we have 125, we apply the multiplication rule. So here, in the first blank, you have 5 letters to choose from the word smoke. So for the first letter, you have how many choices? You have five choices. For the second blank, since repetition is allowed, you still have five choices. For the third blank, you still have five choices. So 5 times 5 times 5, we are using multiplication rule. So we have 125. Okay? If if the problem can be done using the multiplication rule, it's a bit easier because sometimes we forget the formula. We forget the formula. Note if there are n items to be arranged and only r items are taken at a time and no item is repeated, the number of permutation is computed by using this formula. So this is the formula that we have, no? That's the formula that we use, this one, in computing the number of permutation. Again, you have to take note that we are going to take our objects from N. But if repetition is allowed, just apply the multiplication rule. Okay? Next. Again, we have another example. A zip code contains 5 digits. How many different zip codes can be made with the digits 0 to 9 if no digit is used more than once and the first digit is not 0? Is not 0. So the first digit here is coming from the numbers 1 to 9 because it's clear in the problem that we cannot have 0 as the first digit of the 5-digit numbers to be formed. Okay? For the first position, there are 9 possible choices since 0 is not allowed. Okay? I've said that one already. After that number is chosen, there are 9 possible choices since 0 is now allowed. So 0 can be used in the second, third, fourth, and fifth. Then there are 8, 9 times 9 times 8 times 7 times 6. Why is this? Okay? So there are 8 possible choices. Then 7 possible choices and 6 possible choices. Okay. Let's have it using the blanks that I've just introduced. So let's have 1, 2, 3, 4, 5. Okay? Because we are going to make 5-digit numbers. So for the first digit, for the first digit, you have to, for the first digit, you have 9 choices. 9 choices because you actually have 10 numbers, 0 to 9. But since 0 cannot be our first digit, you only have 9 choices. But for the second, third, fourth, and fifth digits, you can use 0. So for the second digit, you still have 9 choices. Okay? So it's like here. For the third digit, only 8 choices are left. Then 7 choices. Then 6 choices. That's why you have this. So taking product, you have 27,216. Now, using the permutation rule, I don't have to erase anymore because the the prints on in white are clear. Now, we can't include the first digit in the formula. Zero is not allowed. So that's already mentioned. Okay, so you have 27,216. If you are going to use the formula, the permutation formula, it should look like this. So you have separated 9 here. Okay. Then instead of 5, you only have here 4. That is because uh, one of the digits is right here. That's already used. So only 4 numbers are to be added to the first digit. That's why it should have look like this. So you have to understand, no, if how to how to use the permutation formula. Okay, next. Let's come to combination. Combination refers to the number of ways a set of items or objects can be arranged. However, the order is not considered. Likewise, the number of combination for a set of n items taken at a time is always 1 because the order is not given importance. If n items are arranged are at a time, an order is not considered. This is our formula. So, the number of combinations of R taken from N is equal to N factorial all over N minus R factorial times R factorial. Okay, where N is the total number of objects, R is the number of objects selected. Okay, let's have a sample problem. In a lottery, each ticket has 5-digit numbers using 0 to 9. You win if your ticket has the digits in any order. What are your chances of winning? Second condition, you would win only if your ticket has the digits in the required order. What are your chances of winning? For the solution, there are 10 digits to be taken 5 at a time. Now, in problem A, in the first problem, the order is not required. Meaning to say, if the winning number has the digits 1, 2, 3, 4, 5, okay? Those are the numbers in the winning number. And suppose you have the numbers 5, 4, 3, 2, 1. In that particular situation, you win because the order of the 5-digit numbers is not required, is not required, no, in any order, as long as the same numbers in the winning 5-digit numbers. Okay, so we have to use here combination formula. So you have the number of combination of 10 numbers using 0 to 9. 5 at a time is equal to 10 factorial over 10 minus 5 factorial times 5 factorial. So you have 10 factorial over 5 factorial times 5 factorial. This 10 factorial can be written 10 times 9 times 8 times 7 times 6 up to 5 factorial. For the purpose that we have to cancel this 5 factorial and the other 5 factorial in the denominator. So only one 5 factorial is left at the denominator. Then for the numerator, 10 times 9 times 8 times 7 times 6, that is equal to 30,240. Then this 5 factorial is equal to 120. So 30,240 divided by 120, that is equal to 252. Therefore, the chance of winning is 1 out of 252. 1 out of 252. Or you can write that one as 1 over 252. Get the decimal equivalent and convert the decimal to percent. You could see how slim in winning this game. For problem B, we get the idea that the order of the numbers is required. So let's use the illustration I mentioned in letter A. If the winning number is 1, 2, 3, 4, 5, and your number is 5, 4, 3, 2, 1, for that situation, you cannot win because order is required. So for this, we have to use permutation formula. So we have this one, the number of permutation of 10 numbers taken 5 at a time is equal to 10 factorial over 10 minus 5 factorial. So 10 minus 5, that is 5 factorial. Then for the numerator, this 10 factorial, you can write this one, this 10 factorial as 10 times 9 times 8 times 7 times 6 up to 5 factorial. So we can cancel this one. So all you have to, or what you have now is the product of 10 times 9 times 8 times 7 times 6, that is equal to 30,240. Meaning, the chance of winning is 1 out of 30,240. So, it's very, very slim. Another example, a box contains 3 white balls, 4 black balls, and 3 red balls. Find the number of ways in which 3 balls can be drawn from the box such that at least one of the balls is black. Okay. In our solution, you have to take note of the quantifier at least. At least one ball is black. At least. What is our condition here? You have to draw from the box how many balls? 3 balls. Okay? But at least one of the 3 balls is black. That's the condition. We have to satisfy this one. So in this illustration, we have to use combination. Okay, so one black and 2 others. So the combination of 4 taken 1 at a time times the combination of 6 taken 2 at a time. So let us understand why we have the combination of 4 taken 1 at a time. Okay, let's go back to the given. We have here that we have 4 black balls. Okay, this one. That's why we use this one. Then, for the two others, this one, two others, you have 6 taken 2 at a time. Okay, so for this one, this is the equivalent. Then this one. Okay, so 1 factorial is just equal to 1. Then 4 minus 1, that is 3. So 3 factorial. So in here, 4 times 3 factorial. Then you can cancel 3 factorial. 3 factorial in the numerator and in the denominator. So in here, what is left here is just 4. And in here, 6 factorial, you have 6 minus 2 factorial. So that is 4 factorial. So in here, in the numerator, you only have 6 times 5 times 4 factorial. For it to be cancelled, no, the 4 factorial in the numerator and the 4 factorial in the denominator. So what is left is 2 factorial. So you have 6 times 5, 6 times 5, right? You have 30, 2 times 1, this is 2 factorial is 2. That is 2 and 30, so 15 times, that is 30 divided by 2, that is 15. So this one is 15 here. Then this one is 4. So that's why 4 times 15, that is equal to 60. Then another 2 blocks and 1 other 2 blocks. So you can see here, so the combination of the 4 black balls, you have 4 taken 2 at a time. So the same process here. For this one is just equal to 6. And this one is also equal to 6. So you have 6 times 6, you have 36. Then all 3 blocks. So you have to take the combination of 4 black balls, taken 3 at a time. So that is equal to 4. Now, take note, the quantifier, at least one of the balls is black. So we have to take the sum of the 3 combinations. Therefore, we have to get the sum of the combinations, 60, 36, 4. That is equal to 60 plus 36, that is equal to 96 plus 4, that is equal to 100. Difference between permutation and combination. The major difference between the permutation and combination are given below. Permutation means the selection of objects where the order of selection matters. For the combination, selection of objects in which the order of selection does not matter. Meaning to say, in combination, it is about the composition of the elements. The composition of elements. So for example, we have A, B, and BA. That is just one combination. The numbers 1, 5, 5, 1, that is just counted as one combination. Because the order of the elements or the selection is not required. Now, for the second comparison, in other words, it is the arrangement of R objects taken out of N objects. So, it's the order. Under combination, it is the selection of R objects taken out of N objects, irrespective of the object arrangement. Okay? So, that's the difference between permutation and combination. Permutation requires the order of the selection, the order of the elements, while in combination, it is just about the composition. And these are some of the exercises for you to practice. Thank you very much for watching.